Another test that can be used to determine whether a series converges or diverges is known as the integral test. The integral test is based on the idea that we can use a continuous function and therefore use an integral of a continuous function to approximate the behavior of a discrete series. Let's consider the example of a function that is positive, decreasing, and continuous. We will call that function f of x. Now, we keep it positive to make our lives a bit simpler, much like in the divergence test, we saw series that all the terms were positive. We need it to be continuous in order to get away with using an integral. And we need it to be decreasing because, as we saw in the divergence test, the only possible way that a series can converge is if the terms drop to zero. Now, that doesn't guarantee convergence, but it's the only way to have a chance at it. So, let's consider this function subdivided into intervals of width 1. So an important thing to realize here is that if we're using width 1, that means that delta x is equal to 1. Now we're going to do two things with this. One is we're going to draw rectangles on each subinterval. First, with the idea of inscribing them. Now, because this is a decreasing positive function, that means we're going to be using the right endpoint of each interval to determine the height of the rectangles. The idea then is that the height or the area of each rectangle is going to be equal to a term of the series. This first rectangle has a width of 1 from its delta x and has a height equal to f of 2. The second rectangle has a height equal to f of 3. The third rectangle has a height equal to f of 4. And the n-1th rectangle has a height equal to f of n. Since delta x is equal to 1, the area of the ith rectangle is simply going to be equal to the value of the function at that value, starting at 2 and going up to n. Note that we did not have a rectangle whose height was based on x equals 1. The first rectangle's height was based on x equals 2 to give us a value f of 2. Now, an important thing to notice is that the full area of this region goes all the way up to the curve. But the areas of the rectangles do not go up that high. Each rectangle is approximating the area under the curve, but each rectangle is underestimating it. So if I add up the areas of all of the rectangles, from 2 to n of a sub I, this is the sum of each of the rectangles. that would be less than the area from 1 to n under the curve. Because each rectangle is underestimating the actual area under the curve, the sum of all the rectangles would be less than the actual area. Now we're going to look at the same situation, the same curve, a continuous decreasing curve, still with subdivisions of width 1. This time, however, when we build the rectangles on each subinterval, we're going to build them off of the left endpoint. By following much the same procedure, the height of the first rectangle is going to be based off of f of 1, the height of the second rectangle based off of f of 2, the height of the third rectangle based off of f of 3, and so on to the last rectangle, which is going to be based off of f of n minus 1. Since the width of each subinterval is 1, the area of the ith rectangle is equal to the value of the function, this time for I equals 1 up to n minus 1. Now the actual area under the curve is this region in pink. However, the rectangles, because they're based off of the left endpoint of each subinterval, each rectangle is including a bit of extra area above the curve. So that each rectangle actually is overestimating the area of the region. Thus, the actual area of the region is actually less than the sum of the areas of all the rectangles. So what we have here is a neat little inequality. We have from 2 to n as an underestimation of the area, and then we have from 1 to n minus 1 as an overestimation of the area, so that the actual area is somewhere in between. Now, we're going to put this in terms of a partial sum, since each of these is currently a finite series, and the region is finite since it only goes up to n. It makes sense to say that S sub n is equal to a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. But as we see in the graphs, a sub I is equal to f of I. So a sub 1 is the same as f of 1, a sub 2 is the same as f of 2, a sub 3 is the same as f of 3, all the way up to a sub n, which is the same as f of n. Based on this, the two series up here, starting with from 1 to n minus 1, this is the sum of the terms starting at 1 and going up to n minus 1, which is the partial sum of the first n minus 1 terms. The second series, which starts at 2 and goes up to n, is the sum of all of the first n terms, but minus the first one. Since it starts at 2, f of 1 does not actually figure into it. So the first series here excludes the very last term of the partial sum, and this one excludes the very first term of the partial sum. And that allows us to rewrite our inequality as s sub n minus f of 1 is less than or equal to the integral from 1 to n of f of x dx, and that is less than or equal to s of n minus 1. We're going to break this down into two inequalities. We're going to look at each inequality separately. First, we're going to start with s sub n minus f of 1 is less than or equal to the integral from 1 to n of f of x dx. Let us assume now that if we were to continue that region infinitely, not stop at n, but if we were to continue that region infinitely, let us assume then that if this integral converges, so we're dealing with an unbounded region that has a finite area, if it converges, then it has a value to which it converges. And in that case, we can then say that s sub n minus f of 1 is less than or equal to L. Certainly, if the finite region from 1 to n is bigger than this, then the infinite region is also bigger than s sub n minus f of 1. Adding f of 1 to both sides shows that the partial sum, s sub n, is bounded from above. And furthermore, it is monotonic, because if all of the terms are positive, and this is where it was important that the function was positive, we needed it to be continuous to allow us to use the integral. We needed it to be decreasing so that the terms of the series got smaller, so that there was a chance at convergence. And it needed to be positive so that we could say not only is it bounded from above, but it is monotonic, because each new term added on is positive and increases the sum. So this is a non-decreasing sum. Assuming that the function never actually turns horizontal, that it continues to decrease the whole way, as the claim said, then we can be more precise and say that it is an increasing sequence, not stronger than just non-decreasing. It is actually an increasing sequence. But in either case, it is both bounded and monotonic. And as we saw when we spoke of sequences, this means that the sequence of partial sums converges. Now, we do not know the value to which it converges. We did not establish that. All we know is that it converges to a value less than or equal to L plus f of 1. There's a lot of wiggle room values that are less than L plus f of 1. So we do not know the value to which it converges. We simply know that it does. So if the integral converges, then the series converges. Now we have a second side of the inequality as well. The integral from 1 to n of f of x dx is less than or equal to s sub n minus 1. This time we're going to assume that the integral diverges. So when we allow the region to extend infinitely, suppose we find that the region diverges, meaning that it does not approach a unique finite value. Being that the function is positive and decreasing, this would mean that the area is infinite. What that means then is literally that. As n approaches infinity, the integral from 1 to n of f of x dx also approaches infinity. Well, according to this definition we have up here, then as n approaches infinity, in the inequality, the integral would approach infinity, but we know that s sub n minus 1 is bigger than it. Thus, the limit as n approaches infinity of s sub n minus 1 is infinite, and thus the sequence diverges. And thus, the series diverges. So if the integral diverges, then the series diverges as well. And that's the conclusion that we have here. The integral test starts with the idea of a positive, continuous, decreasing function. Now, as drawn in the graphs before, we only needed to be doing this for x is greater than or equal to 1. And then we have a series whose terms of the series are equal to the values of the function at those integer marks. If these things are true, then the series and the integral from 1 to infinity either both converge or both diverge. Now again, this test is not meant to show the value to which the series converges. Remember that in both graphs, the series was either underestimating or overestimating the area. So we will be able to find the value to which the integral converges. The value to which the series converges is not the same. This test is not meant to show the value to which a series converges, simply whether it does or not. Some examples. Let's consider the series n over n squared plus 1. This is a continuous function. We can look at a graph of it very quickly. This is a continuous function. It is positive. Again, if n is from 1 to infinity, then n is always a positive integer. The numerator will always be positive. And n squared is always positive for 1 from, as long as we use positive integers. And adding 1 to that will therefore still be positive. So every term of this series is positive. Each term will get smaller as we go. And the function itself is continuous. So the integral test applies here. What we can do is look at the integral from 1 to infinity of x over x squared plus 1 dx. So reaching back to when we did improper integrals, we can call this the limit as b approaches infinity of 1 to b, the integral from 1 to b of x over x squared plus 1 dx. A relatively simple integration by substitution. We let u equal the x squared plus 1, so that 1/2 du is equal to x dx. And we end up with 1/2 times the natural log of the absolute value of x squared plus 1, evaluated at b and evaluated at 1. The absolute value is not strictly necessary here because, as we said, x squared plus 1 will always be positive. So what we have is 1/2 times the natural log of b squared plus 1 minus 1/2 times the natural log of 1 squared minus 1, which is, of course, 0. Oh, and of course, the limit in front of the whole thing. The natural log of 0 is, of course, 1. So that second term simply evaluates to be minus 1/2. Oh, excuse me, I made a mistake there. 1 plus 1. In any case, though, that term is a constant. So in terms of the limit, that will be a constant. So what we really have is the limit as b approaches infinity of 1/2 times the natural log of b squared plus 1. And then separate from the limit would be 1/2 times the natural log of 2. As b approaches infinity, the term inside will approach infinity. And as that term approaches infinity, the natural log of it will also approach infinity. So what we end up with is something that approaches infinity minus a constant, at which point the constant doesn't really do much. So this whole thing equals infinity. What this means is the integral diverges. And by the rules of the integral test, thus the series diverges as well. The idea is that while the region is getting smaller, while the function is positive and decreasing, it does not decrease at a fast enough rate to counteract the infinite accumulation of area. On the other hand, suppose our series wasn't n over n squared plus 1. Suppose it was 1 over n squared plus 1. Now, as we already mentioned, n squared plus 1 is always positive, and of course the numerator being 1 is always positive. As n gets bigger, the denominator gets bigger, and thus the terms of the series get smaller. So we do have a positive decreasing series. If we allow it to be continuous, then we can do an integral from 1 to infinity of 1 over x squared plus 1 dx, to which we can put a limit as b approaches infinity in front. Now, this cannot be done with integration by substitution, but it more directly fits the form of the derivative of arctangent. So we have the limit as b goes to infinity of arctangent of x squared plus 1. Arctangent of x, evaluated at b minus the evaluation at 1. So we have the limit as b approaches infinity of arctangent of b minus arctangent of 1. Now, as b goes to infinity, the arctangent will approach pi over 2. And the arctangent of 1 is simply constant. So it's not a matter of approaching, it's actually equal to pi over 4. Thus, the integral converges to pi over 4. So since the integral of 1 over x squared plus 1 dx converges, the series also converges. Now again, it is important to note that while the integral converges to pi over 4, it is unknown what value the series converges to. They do not converge to the same value. The series always either underestimates or overestimates the area. So while the series will converge to a value close to pi over 4, it does not actually converge to pi over 4 itself.